Okay, hi, welcome to Psych 2317. This is Statistical Methods in Psychology, and this is Lecture 1. So the plan for today is to do two things. First of all, we're going to ask the question, why are we doing this? What are we doing this for? Why is it that you are being asked to take a statistics course as a psychology major? And then after we establish that, we're going to do a quick review of a couple of basic statistical concepts. These are things that you may have seen in various courses or various contexts before coming to this class. And those two concepts are, we're going to talk about measures of center, and we're going to talk about measures of variability. And so we'll introduce those concepts, do some quick examples, and go from there. So let's talk first about why we're doing this. I'm going to call this the 30,000 foot view of the course. If you look at our course, not as a student in it, but as someone who, like me, who knows what all the content is that we're going to talk about, why is it that this stuff is important? Where does this all fit in to your education? So we're going to answer the question, what are we doing this for? The primary reason that we're taking this is pragmatic. You're going to take a course in research. That's because behavioral scientists do research. And so to illustrate what I mean by that, I thought we would look at a quick example. So here's a quick task that a behavioral scientist might do. In fact, you may have seen something like this in the past. So your task is to name the color of each word that you see as quickly as possible. Now I'm going to do this under two conditions. Here's the first condition. Here you're presented with some words like this, but remember the task is to name the color. So if I'm looking here, I'm going to start naming these colors: blue, green, red. Now that wasn't too hard. Now, of course, you might have noticed that wasn't too hard because not only were the colors blue, green, and red, but the words themselves were blue, green, and red. So it's an easy task. What would you possibly learn with this? Well, let's do something similar, but under a slightly different configuration. So here, remember, the task is to name the color, and so I start doing that. Green, red, blue. Now, I was able to do it. I was clearly able to say, and let me get my little highlighter here. I was clearly able to say that this was green, and this was red, and this was blue. But if you timed me with a stopwatch, and particularly you timed me with a stopwatch that had millisecond accuracy, you would notice that I was quite a bit slower on this. Now, that might be a curious finding to a behavioral scientist. They might say, well, why is it that we are slower when the words are different than the colors they're printed in? So this has been studied for a long time. This is something called the Stroop effect. It goes all the way back to the 1930s. And this Stroop effect is interesting to cognitive scientists because it says something about how what we read is automatically processed. So the question as a scientist that I would have is, well, how do I understand what's going on here? How do I understand this Stroop effect? And then particularly what we do to understand that is we're going to do research. And the purpose of that research is to do experiments and test some competing models of this human behavior. So the cycle of research then would be to set up an experiment. And so maybe you do something like what I just showed you, but you do it a lot of different times with a lot of different people. And then you measure things. So maybe we measure how long it takes people to read through the list. And using those measurements, we then collect data. And we do this over and over again. Now, what do I mean when I say we test competing models of human behavior? Well, this is where the statistics part comes in. A model in cognitive science and behavioral science more generally is a quantitative instantiation of some observed behavior. So essentially what we're doing with a model, or as modelers, is we are turning the Stroop effect, this thing that we were able to qualitatively describe, we're turning it into something that's quantitative. We're turning it into something that involves numbers. So let's talk about exactly how we do that for this Stroop effect. So we might think about the Stroop effect as the following definition. We're going to say the Stroop effect is the difference in response times between those congruent words that were where the color in the word was the same and the incongruent words. The difference between those response times we're going to define as the Stroop effect. Now, why would we do this? Well, if we define the Stroop effect as a number, that then lets us set up models about that number, our best guesses about what that number is. So for example, model 1, we might say the Stroop effect is 0. That is, model 1 is a model that says there is no Stroop effect. It's just the same. There's no difference between them. But model 2 might be a model that says, yes, there is a Stroop effect and it is positive. So all of those things, all of those best guesses about human behavior can be quantified as two possible models. One where the Stroop effect equals 0 and one where the Stroop effect is bigger than 0. So our primary question as a scientist, as a behavioral scientist, is to say we've got some observed data. Which of these is the better model? 30,000 foot view of the course is that we're going to learn how to answer that question. And that's going to be the tool that we use to do research. So your next question then obviously is, how do we answer this question? How do we decide which is the better model? Well, we're going to do two things. Now, let's see if I can get these in the right spot here. The two things we're going to do in this course is we're going to learn how to describe our data, so all those response times that we got, and then we're also going to learn a little bit later how to make inferences with our data. Now, what exactly do we mean by these two things? Well, by describing our data, we're asking what is the most typical measurement? And that is what we're going to cover in this lecture, in this unit. But we can also ask things like, not only what is the most typical measurement, but how much do we expect these measurements to vary from each other? And that's also something that we'll talk about in this unit. And then finally, we might say, what is the standardized effect size? This will be some new vocabulary for us, and that's something we're going to learn in Unit 2. What about making inferences with our data? Well, what that means is we're going to use the tools of probability theory, which we'll study in Unit 3, to make our best guess about the true magnitude of this effect, which accounts for uncertainty in our measurements, which we'll talk about in Unit 4. And then from there, we're going to learn how to estimate the size of the effect. So that's something we'll talk about in Units 5 and 7. And then finally, we will assess the adequacy of some models of this effect. And we'll learn that using various techniques, including t-tests in Unit 6, analysis of variance in Unit 8, and then finally, rounding out the end of the course, we're going to learn something called Bayesian methods in Units 9 and 10. So this is the 30,000 foot view of what all it is that we're going to learn in this course. In a nutshell, it comes down to we're going to learn how to describe our data, and we're going to learn how to make inferences with our data. And it's going to be a lot of fun. So let's go ahead and get started on that, and this will begin the second part of our lecture. And that is we're going to review a couple of some basic statistical concepts where we do this description of data. So the first, we're going to talk about measuring the center of data. And when we talk about center or central tendency, what we're really referring to is what is the most typical value of that data. And of course, you may know some of this already. This is most typically measured by something called the mean. The mean is just is simply another word for average, and it's something you all know how to do. As a formula, the average looks something like this. Now that may be some unfamiliar notation to you, so I want to talk real briefly about what some of these things mean. First of all, this symbol on the left, this guy right here, that is our symbol for the mean. So let's write a little key out here. So when we see something like that, that little X bar, that usually refers to the mean. Okay, so anytime you see that, you can think we're talking about a mean. Now, the mean is defined as this guy up here, the top, you can't see that, hang on, is this guy up here divided by n. Now, what are those guys? Well, the sum, no, so that's the sigma that you see, that's read as sum often in mathematics and almost exclusively here. We're going to say the sum of the x sub i's, that's just the sum of each data point. So when we say the sum of x sub I, we're saying add up all of the values of x that's indexed with this little variable I. So if you've got like 5 data points, you would call those x1, x2, x3, up to x5. And this is a shorthand that says add those all up. Take the sum of each of those data points. And then take that sum and divide it by n. N is simply the number of data points. Now you may be wondering, why don't I just tell you that the mean is what you get when you add up all the data points and divide by how many there were? And that would be just fine. But one of the things that you're going to learn quickly is that a lot of mathematical concepts are much more easily described if you're able to use some symbols to represent them. And this is a simple example to get us started down that path. And so this is a good formula to get some practice with. Now, that doesn't mean that you necessarily have to memorize the formula. There's a difference between understanding a formula like this and memorizing it. I would much prefer that you understand it. And what do I mean by that? Well, I mean simply, do you know how to compute a mean? And I think the answer that you'll find is, yeah, probably you do. Let's do an example to see if that really is the case. So let's suppose that we wanted to find the mean of 2, 3, 5, 8, and 12. Now let's do it with our formula. So we'll say x bar, again, which represents the mean, is going to be the sum of the xi's divided by n. Okay, so we'll talk about what each of these is. First of all, the numerator, the sum of the xi's. Well, that's just the data points added together. So this is 2 plus 3 plus 5 plus 8 plus 12. And we're going to divide by n. N is the number of data points. In this case, we have 5 distinct data points. 1, 2, 3, 4, 5. Now, let's figure out what that sum is. So we got 2 plus 3 is 5, plus 5 is 10, plus 8 is 18, plus 12 gives us 30. And then we divide by 5, and that gives us a mean of 6. So the most typical value of this data set, defined as the average or mean of this data set, is 6. And that's how you compute a mean. This should not be surprising to most of you, but that's how it's done. We're going to use that here in just a little bit, but that is sort of the first step at describing the most typical value. The other way that you can measure the center or the most typical value of a set of data is with the median. Now, what is the difference between a mean and a median? Well, the difference comes in the definition. The median is the middle number. It's not the average, but rather it's the number that's smack dab in the middle, assuming that you put the numbers in order. This is a critical assumption. You have to put the numbers in order first before you can compute a median. So for example, this actually, there's 2 different things that can happen here, so I want to walk you through both of those. If there is an odd number of data points, so like the example that we just did, we had 5 data points. In this case, the median will be the unique middle number. What do I mean by the unique middle number? Well, let's practice computing the median. First of all, check your data points to see, are they in order? And from left to right, you can see that they certainly do increase. So we've already got that taken care of. Now, to find the middle, you can eyeball this, but I find it a little bit better to do it systematically. What I can do is just cross off the ends and start working my way in towards, so I cross out the first and the last, and then after crossing those out, the first and the last, and what I'm left with is 5. And so this is my median. And it's the unique middle number. That means it's the only one there. If I have an odd number of data points, that's guaranteed to happen. Oops, delete that. Now, what if I don't have an odd number of data points? What if instead I have an even number of data points? Well, that's not too hard to deal with either. Let's do a slightly modified example here. Here I've thrown in an extra number. I threw in a number 6 in the middle. So let's look at them real quick. Notice that I've got them all in order from left to right, 2, 3, 5, 6, 8, and 12. Now let's do that same thing. Let's start crossing off the ends. So cross off the 2 and the 12, and then the 3 and the 8. And now you'll notice that I have 2 numbers left in the middle. Well, this is not, so what is the median here? Well, I can no longer say it's the middle number because I have 2. So the solution is we take the average of the 2 middle numbers. And so from here, our median would be the average of 5 and 6, which is just right in the middle. It's 5.6. 0.5 in this case. So median, put the numbers in order, and then you've got to decide, do you have an odd number or an even number? And whichever of those situations you find yourself in, you do the appropriate action. If it's an odd number of data points, you find the one middle number. If it's an even number, you find the average of the two middle numbers. So that covers measures of center. Now, if you remember from the very beginning of the lecture, we also talked about measuring variability. So that's the last thing that we're going to cover today. So what do we mean by measuring variability? What we mean is we want to answer the following question. We want to ask, how much on average does each number differ from the most typical value? That's what a statistician means when they say, I want to measure the variability. They say, how much on average does each number differ from the most typical value? So what I've done here on the screen already is I've put my data points. These are the same ones that I've dealt with for the last couple of examples. I put them in order, but I put them vertically. And there's a reason for that, because I'm going to do some things that are going to be much easier to do if I've got them in a nice tabular format. So here are my XIs, my data points, 2, 3, 5, 8, and 12 put in a column. And down here, you'll notice I also went ahead and wrote the mean, okay? Not the median, but the mean. The mean was 6, as we did earlier. Now, what I want to know is how much on average does each number differ from the most typical value? So what I'm really asking about here is I'm asking about something called, let me change my color, I'm asking about something called the deviations of each data point from the mean. As a formula, what I'm really trying to find out is what's the data point, xi, minus the mean, okay? So for each one of these data points, xi, I'm simply going to subtract the mean, and that's going to give me a measure of its deviation from the mean. So let's go through and do those real quickly. So if I start with the 2 minus the mean, so 2 minus 6 would be a negative 4. This is a deviation of negative 4. That means that this point, 2, is 4 units to the left or below the mean. As of course we can see, if you think about that on a number line, that makes sense. What about 3? 3 minus 6 is negative 3. That means that that data point is 3 units to the left or less than 6. 5 minus 6 is a minus 1. And I just continue doing this all the way through. 8 minus 6 would be 2. Notice the deviation is positive here. That means that that data point is bigger than the mean by 2 units. And then finally, 12 minus 6 gives me a deviation score of 6. So these are my deviations. These are the differences from the mean for each of my data points. Now my question, I think I can answer. My question is, how much on average does each number differ from this most typical value? Well, here are the deviations. So based on the question that I have asked, it would make total sense to find the average of these, which we know how to do, right? That's pretty exciting. So if we add these up, taking into account the negatives and the positives will cancel. Let's see, negative 4, negative 3, and negative 1, that's a negative 8. And then 2 and 6, that's an 8. So I add negative 8 and 8, and I get a strange thing. I get an average deviation of 0. If you need to, pause the video and check that again. Add those deviations up and divide by 5. You're going to get 0. Maybe that is, as I've written here, that is not helpful at all. What on earth has happened here? Well, it turns out, folks, and you can prove this mathematically, that if you do what I just asked us to do, that is, you find the average deviation for any data set, this is exactly what's going to happen. You're going to get an average deviation of 0. And if we want to use that as a measure of variability, that's probably not a good approach at all, because it's telling you there's 0 variability, which of course we know there's not. We know there's a lot more variability in these data points than that. So what's going on here and how can we fix it? Well, clearly what's going on is we're getting some negative numbers up here, and we're getting some positive numbers down here, and they are canceling out when we add them. So what we need is a slick way to ignore the negatives, to get rid of them. Now, the mathematically astute among you might say, well, just take the absolute value, and I love that approach. The problem is down the road, it'll make our lives more complicated if we do that. So I'm going to say let's not do the absolute value right now. And let's do something slightly different. So while I'm making up another column in my table, I'm going to let you think, and if you need to, pause the video and ask yourself, what could I do to every number systematically? Something that I could do to every number that would always make the result positive. And then when you think you got the answer, start the video again. Okay. All right, so do you think you have the answer? Well, if you said square them, you're absolutely correct. That's what we're going to do. We're going to take these deviations, xi minus x bar, and we're going to square each of them. That's going to be the trick. That's going to be the thing that helps us out tremendously. Okay, so let's do that. All this amounts to is just taking each of those deviation scores, -4. My cat's trying to get in the video, so I'm going to make him go do something else right now. We're going to take each of these deviation scores and square them. So -4 squared is going to be a positive 16. Remember, squaring always gets rid of the negatives. So -3 squared, that's 3 times 3, which is 9. -1 squared will give us 1. 2 squared will give us 4. And then 6 squared will give us 36. Now, let's find the average of these and see what that gets us. Okay. Well, how do we find the average? Well, we add them all together. So that's going to be 16 plus 9 plus 1 plus 4 plus 36. Okay. And we're going to divide that by the number of points, the deviations. We got 5 of them. Okay. And so let's do this. We got 16 plus 9, which is 25, plus 1, which is 26, plus I'm all messed up here. I'm gonna do this a slightly different way, guys. Sorry about that. I'm gonna take 9 and 1 is 10, and 16 and 4 is 20. So that's 10 and 20, which is 30, plus 36, which gives us a total of 66. Okay. You can do the math however you want. I don't have a calculator sitting right in front of me, so it was a little easier for me to do it that way. And then we're going to take that and divide by 5. And if we do that, I think that this gives us 13.2. Let me just check that real quick. 66 divided by 5 is exactly 13.2. Okay. So the average squared deviation here, and let's write down exactly what that is. That is the average squared deviation is 13.2. So maybe somehow that will be a good index of variability. Turns out that it totally is. In fact, we give it a special name. It turned out to be quite useful. We call that the variance. And so based on this, we define the variance as this average squared deviation. In fact, you can write down a formula for it. The formula is usually pretty scary in a first stats course, but I want you to realize that this simply indicates what it is that we did by hand in that table. We added together, let's put all these together, we added together the squared deviations and then we divided by n. So don't let the formula scare you too much. It's nothing more than a shorthand for exactly what we did. So we weren't able to do this, which was find out how much each number differed from the most typical value, but we got close. We got close as in terms of how much the squared deviation is from each typical value. Okay, so I don't know, is that useful or not? Well, let's talk a little bit about that. So for this data set, let's wrap up here. For this data set, 2, 3, 5, 8, and 12, we found a variance of, well, it turns out 13.2. Okay, so what exactly does that mean? Well, remember, this variance is supposed to measure the average distance from the most typical value. But clearly, this is too big to be a measure of that, right? The values themselves, they don't differ from each other by 13 points. This is just too big. What's the problem here? Well, the problem, of course, that you've probably already seen is that in the beginning, when we were working on this, to circumvent the problem of averaging deviations, we squared the deviations first. And so now, instead of having an average deviation, we have an average squared distance, an average squared deviation. So the solution here is to get out of that scale, which is the average squared distance, and undo the squaring. How do you undo a squaring? Well, you take a square root. And that's what gives us the final definition for today, which is something we're going to call the standard deviation. And the standard deviation is nothing more than the square root of the variance. Even though, if you look in any old textbook, and my textbook is no different, if you look in any old textbook, you're going to get a definition of standard deviation that looks just like this. And I don't know about you, but depending on how comfortable you are with mathematical formulas, this might be one of the most scary ways to begin a statistics course. But it's nothing to be scared of. It's nothing more than the square root, there's that, of this thing, which is the variance. What was the variance? Well, it was the sum of the square deviations divided by n. It was the average square deviation. So how do you compute a standard deviation? Well, it's pretty easy. We've already done most of the work. For the data set 2, 3, 5, 8, and 12, what is a standard deviation? Well, by definition, the standard deviation is the square root of the variance. Do we know the variance? Well, sure we do. We found the variance earlier. It was 13.2, that average squared deviation. So what do we do with that? We just take that square root, and if we do that to 2 decimal places, we get a standard deviation of about 3.63. So this tells us, on average, the data points differ from the middle by about 3 to 4 points. And if you look at the points, the data points 2, 3, 5, 8, and 12, that's more like it. We know the mean is 6. So on average, the points here, 2, 3, 5, 8, and 12, they're around 3 to 4 points on average away from that middle. So today, we talked about what's the course good for, and hopefully you buy what I'm saying. It is true. What do you do in this course? Well, one of the first steps is to describe data, and the first steps of that is to compute means, which measure the center, medians, which also measure the center, different type of center, and then finally variance and standard deviation, which are common measures of variability. So if you can do those, you can describe data. So the next step will be to do some practice with this, which we'll do in other sessions. But for now, that's it, and I will see you at the next lecture.